Thank you. Thank you everyone for being here, and thank you for the invitation and the organization of this workshop to Joan and Chaviros and Dominic. It's very nice to be here and to have seen all of the talks. Okay, so I'll talk about. I I have to apologize to Joan and to Eric, who've heard me speak about this multiple times, and I'm gonna have to repeat many things because I think it's maybe nicer to review some of the things that were seen in two previous talks so that everyone is kind of on the same page and everyone really understands what is the novelty of these particular neural networks, what are potentially the interesting mathematics. And some of the slides are a bit cut and paste because I want to talk about some stronger results than what we used to do in the past. So it's series of works with multiple people. In particular, I have to put the accent on Philippe Rigolet and also Hugo Kubik, who is my student now. And so really, this is going to be the equation. I'll end up really being interested in just this very innocent looking interacting particle system. So we have n particles on the unit sphere, and they evolve over time by following this very particular convex combination of all particles, okay? This is going to be the model of interest. And my goal in the first part is to tell you why studying this system is actually interesting. So I think everyone knows that transformers are pretty relevant nowadays in machine learning and AI in general. And probably one of the first paradigms that changes with respect to standard neural networks and transformers is the data. As it was already presented by Andrea Agazzi in the first day, because transformers were developed for text, and text is typically sequential data. Okay, so there's correlations between different elements in one data point. So one data point is a sequence of text. This is a cartoon, but you should think that in practice, this could be, I mean, your database is going to be the entire internet, and one web page is one data point. Okay, something of that form. But let's think of just sentences for simplicity. And so what you're going to do is you just take your sentence, you parse it into different words. Typically, it's smaller than words, and you embed each word into a d-dimensional vector. And one should think of d as being of the order of thousands. So I don't know what. So 2 to the power 10, maybe something like this. So typically it's powers of 2. You should always think of powers of 2. And one particular thing that we do to the data is that we add a positional encoding, meaning that the word the over here and the word the over here is not going to be represented as the same vector. Okay, so we'll really label the position. As Andrea said, you can just think of this as saying that my vector in RD is going to be the along with 1, quick along with 2, etc. Okay, this is the easiest way to think about it. In practice, this is done in an overly complicated way, and I want to get into details. And the terminology that people use is that each embedded vector is called a token, and when you write this thing, it's called a prompt. Okay, so prompts is what you write to ChatGPT, for instance. Okay, and then people understood, of course, as things go in machine learning, you have a hammer and you have a nail. Everything is a nail. So people then understood that you can also do vision with transformers. And the idea of doing vision is that you take your image, and instead of treating the image as a big d-dimensional vector as it was presented in the previous days, like John said, what you're going to do is that you're going to patch this image. So you do like domain decomposition in some sense. You patch this image, and each patch is going to be a token along with its positional encoding. Okay? And this is one data point. Okay? Think that there's going to be, of course, a big data set of data which you're going to work with. This is just one data point. So the thing I'm going to be interested in, I have to really emphasize this, is that I'm going to be interested in just looking at the equations for what transformers are, and I'm not going to care about training. So the thing to know in deep learning, machine learning, everything is that there's multiple stages of what's going on. Particularly, you have a model, so a neural network, but this neural network has parameters, and you train these parameters on data, meaning that you typically have you have n data points. So as Jean presented, you can think of just supervised learning in which you have labeled examples, and then you just define some loss function on these data. So you can do regression if you want. and you try to find the parameters, the weights, to minimize this loss. Okay, and typically you do this by doing some gradient descent method. Now, everything I'm going to talk about is going to subsume that I'm in the case in which the model is trained. Okay, meaning that the parameters are given to me. I'm not going to focus on training. I just take a train transformer, which is already pretty complicated to understand. I'm just going to try to see if I give it a prompt, what is going on with this prompt over the different layers. So, what is a transformer? I'm going to try to write as fully as possible all the equations. And essentially, if you look at the code, whatever code you can find, but this is really kind of the crux of the matter, it's something of this form. Okay, so you're doing a discrete time iterates. The time here is the role of the layers. Okay, so there's no training. Forget about epochs. This is just the layers of the network. And so you're doing essentially three main operations. Okay, and for the experts in the room, the things I'm not going to deal with is masked attention. I'm not going to talk about this. And I'm not going to talk about multi-heads because this is also a bit of a complications. And I'm not going to talk about particular positional encodings, but everything else I will try to say. And so what are we doing? We're doing this first. I have let's say at layer T, I have my T tokens. Okay, so think of T is equal to 0 if you want to just start. And how do we evolve them? We do this convex combination of all of the guys. Okay, so these guys are between 0 and 1, these exponential BT over the sum. Then we have a matrix VT, and then we add xi to all of this. We get a first iterate, which is yit. Okay, so I do this for every element in the sequence. I is the label of the element in the sequence of the token, and T is the layer. And then what I do with this is I take this guy and I plug in inside a standard network. Okay, standard neural network. This is just a perceptron. Okay, with ReLU activation with parameters W, U, and B. And I normalize everything so that everything is of norm 1. Okay? In practice, there's tweaks here, but to idealize, you can think of that you're just dividing by the norm. Okay? And so this network has parameters, as I said, things that are trained, but for us, they're given, they're fixed. And the parameters are what? Are BT, which is typically factorized in practice to have this Q and query matrices, so QT, KT, as you saw already in the talks. Because for me, everything is trained. Of course, I don't really have to look at two different matrices. I just look at the product. I have this matrix VT, and I have this WT, UT, and BT. Okay? Now, when I see this, of course, I just, again, because working in discrete time is not always very convenient, you just want to abstract this away and try to find some kind of a continuous time analog. Okay, so maybe I just rescaled things here. I add a delta t in front of the VT, a delta t in front of the WT, and I try to see what happens when DT goes to 0, right? Okay, so there is a bit of a catch here, I have to say. And this may be important to say because Link asked the question on Monday. So I have a DT which goes to 0. And this is a bit of a spoiler. I'm not going to get into details, but you can get an ODE. This is for those who know, this is a splitting scheme. Okay, it's a Lee-Trotter splitting of this ODE. So when delta t goes to 0, we get this Lee-Trotter splitting. So this is the ODE we get in the limit. Okay, but there's an assumption that is made here, and the assumption is that all of these guys, VT, WT, UT, BT, they don't have to be continuous. You need them to be bounded, but what matters is that they're deterministic. Okay, so these guys are we to have this ODE in the limit like this, we assume that these guys are deterministic so that we can do deterministic numerical analysis. But in fact, when you train a neural net, you always start with random initialization. Okay, typically everything is independent Gaussian. So when you run your training algorithm, these guys stay random, of course. There's correlations that arise, but what really matters is that they're random. So actually, when you want to get a continuous time model, you have to take this randomness into account. So in fact, the limit equation you should get when delta t goes to 0 is not always going to be the same depending on how you scale delta t and the number of layers. Okay, so here I'm working in a bit of a simplified case. So we assume that we just have the ODE in the limit. but typically you have to do things from stochastic calculus. You have to use stochastic calculus to really get the full array of different possible equations. But just to spoil you, I'll not get into details because this is ongoing work. There's going to be a lot of papers on this in the coming 3 weeks. I promise you. I know multiple people are working on this. But essentially what you're going to get is that even when these guys are random, okay, when they're random matrices for every time, what you're going to get is a deterministic part, which is exactly this guy. But here, in fact, you're going to take an expectation over the parameters, okay? And then you have noise. And this noise is very complicated. I'm not going to get into details, but this is using, for those who know, it's using tools from stochastic modified equations. So this is something that Eric used to do in his past life. Okay, anyway, this is what we're going to consider, okay? This is our equation. And this projection is so that I always stay on the sphere, okay? Now, okay, I don't care about this. Now, as I said, for me, these parameters are given, okay? All of these parameters are given. And the thing you all immediately observe here is that I have, it's a splitting scheme, so I have two parts, right? I have two elements in this vector field. I have this AB, which there's this hidden mu t, which is written there, which is defined in this way. And then I have this other vector field, okay? The thing with the positive part. The difference between both of them is that you see that in the second vector field, this is a thing that only is applied on xi, okay? So if I'm a particle xi, I only see myself in this vector field. So for people who are more from PDEs, you see this as a lower order term, okay? This is lower order term. Whereas this guy is seeing, if I'm a particle xi, this guy is seeing all of the particles in a very nonlinear way. So this is a higher order term. So, of course, now we're going to try to do math. So you're going to try to oversimplify this equation reasonably. And the first simplification I'm going to make is that when you study, say, PDEs, you study asymptotic behavior of PDEs or ODEs, the first thing you do is you study first what happens with the higher order term. So I'm just going to remove the lower order term. For the rest of my talk, I don't care about the MLP. We can discuss this later. So I'm basically gonna say that WT is equal to 0, okay? So that's kind of the story I wanted to say. Now, when you look at this equation, I mean, you may naturally ask yourself the question, why in the hell did people in machine learning think of doing this? Like, how did they come up with this super complicated formulas to do language processing? Why? Now, I obviously don't have the answer exactly as to why, but I have some hints, and I'm going to try to explain to you what I understand in terms of why. So the first thing is already something that INRIA hinted at, is that because of the fact that we have positional encoding, we don't care about the order of the particles in the sentence, okay? Meaning that we really work just with the set. And a set of points is always in projection with the empirical measure, right? And I can always define the empirical measure of the particles over time, and this empirical measure solves a PDE, okay? In the weak sense. This is just chain rule in integration by parts. And the nice thing about this PDE is that this PDE makes sense for arbitrary measures, right? So this is a strict generalization of the ODE. Because if I look at the PDE with empirical measures, this is exactly equal to the ODE, but this is something that is more general because it makes sense even for general measures. And let me comment for the people who care about, here we have Cauchy-Lipschitz, okay? So there's no problem with Wolff-Bosenis. We're on the sphere, and this vector field is as smooth as you want. It's exponentials. Okay? So in this sense, you're immediately conditioned to look at transformers as very particular flow maps, which take as an input a probability measure. It's always an empirical measure in practice, right? Because you always have discrete, you don't have infinitely many data points, infinitely many tokens in one data point. But it is a measure, and it spouts out a measure at the end, right? Because you're going to do iterations of this. you're going to basically solve a discretization of this PDE, of this ODE, and you're going to get, again, some empirical measure at the end, okay? Of course, it's not any flow map. It's a very particular map. But the question is basically, you can ask yourself, the question is, what kind of a flow map do I need to solve tasks? And then why do I pick this particular flow map? Okay? So maybe let's be a bit more concrete. Try to say what kind of task you're trying to solve with these models. So as I said, I'm not working with, for the experts in the room, I'm not working with masked attention, meaning that ChatGPT is not the model I'm explaining here. I'm explaining things more like BERT, so somewhat easier. But the things you can do with these models are things like masked language modeling. It's a task I like a lot. So masked language modeling is the following. You consider your data set of, let's say, sentences, and you take your each sentence in your list, and you're just going to hide one word in the sentence. You're going to replace it by the token mask. You're going to do this with every sentence in your data set. You take your mask token as a target, and you're going to try to do the matching problem of all of the inputs to all of the outputs. Okay? So this is by definition a measure-to-measure problem, right? You're trying to map a sequence of capital N probability measures, which are empirical measures, to capital N point masses. Okay? In practice, it's not just going to be point masses. You're going to hide more words, but this is just to idealize what's going on. Okay? So this is the fundamental questions we're trying to solve with these models. Are always all of the tasks that people are trying to solve is that you have a data set of N probability measures, which are structured. Okay, they're not arbitrary probability measures, inputs and outputs, and you're trying to do the matching problem. Okay, so you can ask yourself the question, why this map, right? Why do I use this particular transport map? So I have N measures. Okay, so I have N measures. My data set is, let's say, mu1, mu0i. Let's actually write them like mu I and nu I. Okay. So each of these is a probability measure. This is a sentence. I hide one word, and this is the target. Okay. And what I want is with this PDE, these parameters, goal is that mu I of capital T. So this is the solution with initial condition. This guy at time 0 looks like, in some metric, this is your loss, like nu I. And this is for any I. This is what you're doing by training. The fundamental question is this. Of course, capital N is very large. This is not fixed, but okay, this is for sake of simplicity. Now, why do you do that? Why are we using the equation dt mu, plus divergence of this v theta mu t, mu t? This is our equation. This is the transformer, and the vector field v theta is equal to the projection of the integral of the exponential of beta b. So there's a v here, b x y over the partition function okay. So when you try to solve a task like this, it's a task of transportation of measure. Of course, the first reflex you have, I would have as a mathematician, is you have transportation of measure. Why don't you try to do optimal transport, right? And optimal transport, recall that there's the Benamou-Brenier formula, which tells you what? Which tells you that if I have a measure mu and I have a measure nu, and I want to transport one to the other in the optimal way, the thing I'm going to do is I'm going to minimize among all rho and all v the kinetic energy, right? 0t, sd minus 1, v of tx, rho tx dx. And I'm going to solve dt as a constraint, the condition dt rho plus divergence of v rho equals 0 with the boundary data rho of 0 is mu and rho of 1 is nu. Well, rho of t is nu. Okay? Now, the thing you have to understand in this system, so this is just the optimal way, but anyway, what you're going to do is you're going to try to solve an equation of this form, and you're going to try to find this v, right? This is what Gabriel was saying. There's multiple ways. All of these transportation of measure paradigms are giving you ways to compute v. There's a very important thing in this equation, which you don't have in this equation, and it's a trivial. I'm saying this is a tautology, is that this equation is nonlinear. Okay, it's a nonlinear equation in the vector field, and this gives you something very crucial. Let's say n equal 2. I only have two measures to map to two other measures, and let's say I take two measures which at the input they have overlapping support, and I have two targets that don't have overlapping support. Okay. With a linear equation, I can never do the transport from one to the other, both of them simultaneously. This is because of Cauchy ellipses. You have crossing of characteristics. This is the wonderful thing about the nonlinearity. So this is the first thing I want to say about transformers, is that they are very particular flow maps because they're parametrized by nonlinear transport continuity equations. And then the thing you of course want to understand is, okay, it's nonlinear, but there's multiple ways I can parametrize a nonlinear vector field. Why do I choose this particular one? Why this attention field? So this is what I'm also going to try to explain, but in an even simpler context. Okay. So the results we're going to point to are clustering. So this is, as I said, I'm going to try to look at the asymptotic behavior in time of this model, just so that I understand what's happening with the initial measure, so that way I can understand why maybe people guessed that this vector field is relevant. Okay. And a thing I want to really say is that, of course, there's oversimplifications in what I'm going to do in terms of choices of parameters, but this is done so that, of course, you have nice math, but also because you see this phenomenon I'm going to explain in practical models. Okay, not always, but you often see this kind of behavior empirically. It goes under multiple names in the literature. Okay, so this is what I can show you this, for instance, this simulation, which is a model called Albert. It's a very simplified transformer, but it's a trained transformer by engineers. And the thing that matters in this model is that it's exactly the equation I wrote. Okay, so it deals with exactly the equation I wrote, but all of the parameters are constant in time. Okay, and so we download this trained model from Hugging Face. So you download this and you take one prompt at random. So it's trained on Wikipedia text. Okay, so doing masked language prediction on Wikipedia text. And so here you take one random sample. So maybe it's the web page for Romania, I think. And we take all of the particles and we'll look at their inner products over time. Okay, so for those who are more familiar with kinetic theory, what this is, the plot of this histogram is just the 2-point correlation function. Okay, and so you see what's going on over time. So this model has only 48 layers, and you start seeing that. So it's plotted between -1 and 1 because this is where the inner products take their value, and you start seeing that a lot of the points start concentrating toward 1. So there's a lot of the particles that start becoming the same, okay? Because you're in the sphere, inner product equal 1 means that the points are the same. And actually, if you run it up to time 500, you're going to see that almost everyone is going to go to 1. Okay? So to try to understand this and try to prove some things, this is why I'm considering this very simplified model. So what I'm doing is that in the original model, we had this B, we had this V, of course, we had the MLP part. I'm saying that the MLP part goes away. V is equal to plus or minus identity. And B is equal to identity. Okay? Many of the results I'm going to say can be generalized to much more general cases. This is really just because the math is much cleaner. And people have, of course, generalized this to even time-dependent parameters. I can give you the references if you're interested. What really matters to me is just to see the kind of behavior that's happening. And this is something that is almost generic. So this is our equation. I'm going to write it down. And this is the thing we're just going to try to understand. Okay, so the equation is I have n particles on the sphere, And for me, n and d are going to be fixed, okay, most of the time. I'm going to work for, everything is going to be quantitative. And I have this equation. Okay, and here I might have also a minus sign. It's either plus or minus. The behavior will be very different. This is what I'm going to try to point out. And so we call this the self-attention model because I don't want to call this a transformer. It's a bit of a too much of a ripoff. Okay. So I want to study the long time behavior of this equation. So what do you do when you want to study long time behavior of some equation? You first try to find some function defined over the solution which has monotonicity properties. Okay, a Lyapunov function. The issue with this, okay, there's one very nice thing you can immediately observe here, is that this has a very nice form. Okay, you immediately see that there's a gradient here. This sum is in fact you have the gradient of the log of the sum. But the issue with the log is that it's not, there's still a lack of symmetry, so it's not totally ideal. I'm going to do another trick to try to find a Lyapunov function. The trick is going to be the following, is that when you look at this denominator, this is the reason why you have a log. The complicated part is this denominator. Well, this denominator is actually pretty benign because this denominator, you can always lower bound it by one term. So this is always of order exponential beta. And it's at most of order n exponential beta. So the scaling is typically of the order n exponential beta. So this is a scaling factor essentially. So let's just remove it for simplicity. So I just consider this equation and I put 1 over n exponential beta here. This is a time scale. Okay. And then I have the sum of the exponentials xj. Okay. Now this is actually a gradient. And what you're doing with this is that you're doing gradient ascent. So this is with the plus sign. So plus sign is ascent. And minus sign is descent. Okay. Of this energy functional. Okay. So I focus on the ascent case. I'll tell you what happens with the descent roughly. And the first thing you ask yourself as a question is, okay, I have gradient ascent. What is this supposed to converge to? So you just try to characterize the global maximum of this. This is very easy. This is just Cauchy-Schwarz, which tells you that any configuration of endpoints in which everyone is the same is a global maximum. So if gradient ascent converges to a global maximum, I have exactly the result I wanted to show. Right? This is exactly what this picture was showing. This video was showing. Of course, this gradient, the reason why I say that this is valid also for much more general parameters is, as Eric was pointing out in Andreas' talk, is that of course this gradient picture is general for all parameters as long as b is equal to v. And in fact, the way you should see v is as a preconditioner. So this is true for any b and v. So it's just a preconditioned gradient ascent or gradient descent on the sphere. Okay? And this fact that they depend on time is just changing the geometry over time. So it's very complicated. This is why I focus on the simple case. Okay, but this is cheating because I removed the denominator. So what happens with the real system? I don't care about this system without the normalization factor. Because even though it's a scaling, maybe it's a bit richer than just a trivial scaling n exponential beta. So the idea is that what this tells you, this lower and upper bound, tells you that this thing is never degenerate. So the trick is to put it in the metric. You change the metric, and you define a new gradient, so new metric. So you fix a point. You define a new metric on tx as d minus 1 to the n, which is just the canonical metric, and you reweight it by this. Then our equation is just gradient ascent of the same energy. It's just that this gradient is not the canonical gradient on n copies of the sphere. It's just this new gradient. But this metric is very benign, okay? So we have gradient ascent on the sphere of this very particular energy. So we want to prove convergence. So we just go to what we know about gradient methods. So I'm going to tell you what the story is today. What are the regimes we know how to prove? So the first thing you're going to use is that we work on the sphere. Okay, so there's no issue with cluster points. You know that cluster points are going to converge to a critical point. So it's a question of uniqueness of limits, right? And you have this wonderful theorem of Loyasevich, which tells you that when you have an analytic metric and you have an analytic function, that you have uniqueness of the limit. So for free, we get that any initial configuration is going to converge to a critical point of E. Okay? This is true for any D, any beta, any N, any initial configuration. So now we need to refine this because we don't want to go to a critical point, we want to go to a global maximum. Okay, so there's another result which people in dynamical systems might know, which is saddle point evasion, which tells you that if you have a C2 function, you're generically going to avoid saddle points, bad saddle points, okay? Saddle points in which the Hessian has the wrong sign. And so just using these two theorems for free, we immediately get that almost any initial configuration, you just need to remove a zero measure set. Almost any initial configuration is going to converge to a second order critical point of the energy, so a local maximum. And then what we're boiled down to is proving that any local maximum is a global maximum. And the story for proving that any local maximum of this energy is a global maximum has multiple parts, because so we, meaning myself, Cyril Letrouille, Philippe Rigolet, and Yuri Polansky, we first proved this in any dimension d greater than 2, but we had constraints on beta. Because basically the idea was that you can first work on the circle, okay, meaning that you work on the torus. So the Hessian is very easy to compute, okay? You can compute it analytically because it's t to the n, so you just have endpoints on the torus. You can compute the Hessian, and then you just try to localize. You do an indirect argument. You try to put all of the points in the zone where this kernel exponential beta cosine is concave, okay? And it turns out that the concavity radius of this guy is exactly 1 over root beta, okay? That's the scale of the concavity radius. And this is why we had constraints on beta. Then many people were very smart and they immediately saw this and told us, you guys are idiots. In dimension greater than 3, it's trivial that everything is okay, because how do you prove these kinds of things? How do you prove that local maxima or global maxima? You do an indirect argument, so you try to find a path, right? And on the sphere in dimension 3 is simply connected, so it's very easy to find a path. The circle is not. So actually the circle, so this works by Nicolas Boumal at TPFL and his group. They immediately understood that in dimension greater than 3, it's true for any beta. And so the story stood still for the circle. People didn't know what to do with the circle. We had this range, so it's exactly this. These are old slides. So it's either beta less than 1 or beta greater than n squared over pi squared. And then there's a recent paper by Yao, Poliansky, and Rigolet. This is maybe 2 months ago, where they prove that on the circle, local maxima or global maxima for any beta greater than minus 0.16. So, and they say that it's not true for beta smaller than minus 3/2, something like this. So you see, it's a lot of I wouldn't say elementary, but it's funny combinatorics you can do, and interesting things arise. And I don't really know how to interpret this for negative beta, but anyway, this is the story. So anyway, what I want to say with this is that we know that any D, any beta, almost any initial configuration, we go to the global maximum, okay? This is all this story is telling you. Now, how do we make this a bit more strong, more quantitative? You see there's multiple indices in this line. So this is D, this is beta. Now, if you're taking dimension greater than n, okay, so if you have fewer points than the dimension, almost any initial configuration with probability 1 is going to be in a hemisphere. And the thing with hemispheres is that they provide a nice barrier. It so happens that if you look at the distance of the point that is the closest to the equator it's always going to go farther from the equator over time because you're doing a convex combination, so the hull has to decrease. And in fact, you can bootstrap this argument and get exponential convergence, but it's fake exponential convergence because this lambda, this rate, is of order exponential minus beta. So the characteristic time to reach the global maximum, even in a nice case, is going to be of order exponential beta. Okay, so you cannot expect fast convergence. Okay, you don't have concavity at all. This is a very hilly landscape. Okay, this is the first conclusion you can make. But there's also another interesting thing which I want to say, which is, this is academic, but it's very nice anyway. It's academic because, as we said multiple times, in practice, n, the number of points, is much larger than d. Okay, but of course, as a mathematician, you don't care about this, and you can fix n and try to take d to infinity. And the nice thing on the sphere is that you have concentration of measure. In concentration of measure, a particular thing that it tells you is that if you take a random initial configuration, it's with very high probability the angles, it's going to be orthogonal. Okay, mutually orthogonal points. Okay, and because of equivariance in this equation, okay, you have a very nice system which is permutation equivariant. You're going to maintain the same angle over time. What this means is that I take my endpoints, I look at the angles between these points. It's always it's going to be independent of the label. Okay, so basically what this tells me is that by concentration of measure stability in large dimension, instead of solving n complicated ODEs, I just have one ODE, which is a scalar one. Okay, which is just the equation for the angle. Okay, and this equation for the angle, I can do phase transition diagrams, which tell me that if I take two characteristic particles, I try to say, okay, what is the probability that their inner product is greater than 0.99? I plot this, and this equation is telling me exactly what is the curve of phase transition. It's telling me exactly when this angle is going to be small or big. Okay, and so the red zone probability 1, blue zone probability 0. Okay, so at high dimension, it's very kind of easy to understand this system because you have a lot of equivariances. And this, I have to say, this is specific to the case of having identity here. Okay, the nice thing about identity is that you have inner products, and inner products are much nicer when they're homogeneous. Okay, now let's go to the fun part. So we have convergence to a global maximum. Is this interesting in practice? What would this mean in practice? This would mean that I give you a sentence, okay? Hide a word. Let's say the fox ate the pig. I hide the word fox. And if I converge to a global maximum in very, very fast, what this tells me is that deterministically, I'm always going to spout out one word. Tell you one word, it's going to be wolf, or there's no probability that it's fox or dog or whatever. And so this is not very good in terms of expressivity. But the result, a mathematical result, it's telling you you're going to go there. But it's telling you you're going to go there very slowly. This matters. It's very slow. So what happens actually over time? What is the transient behavior? So to do transient behavior, I'm going to just show you a very academic example. Let's work on the circle. You have 5 points. Okay? But you initialize them in a very particular way. Okay? Not too particular, but kind of particular. And so what you see with these points, I'm just solving this ODE on the torus. What you see, you look at the time, is that, okay, these points collapsed, and the result tells me they're going to go to a single point, but look at the time horizon it takes. It's going to take, I'm not going to run this, I have no time. Actually, I do have time, but okay. It's going to take time 360 so that you go to a single point. Okay, 360. And this is just 5 points in dimension 2. So you can imagine in large dimension with all kinds of heterogeneities what's going to happen. So this is the first thing we observe. Now the second thing we observe is that now, so I told you we're a gradient flow of this energy. Let me remind the energy. E beta of x is equal to 1 to 2n squared beta exponential beta sum I j from 1 to n exponential beta xi xj. Okay? Let me remove beta so that this thing at the maximum is equal to 1. Okay? Well, 1/2, but let's say it's equal to 1. Okay? can just remove the 2 too. So that the maximum of this is equal to 1. And now let me plot this energy along this trajectory. And let me speed up the clock so that I reach the goal maximum equal to 1. And the speeding up is going to be relevant. And so actually what you see is this very particular graph. And when beta grows larger, so this is beta equal 500, this is beta equal 4,000, this curve is starting to become very steep. It's piecewise continuous, actually, discontinuous. So there's a lot of works in this direction in the, I mean, it's very different context, very similar. Jean also has works on this, which is called saddle dynamics. It's for training simple neural networks. It turns out because the landscape is very non-convex, what you do is you jump from saddle to saddle before reaching your global minimum or maximum, depending if you do ascent or descent. And numerically, we see that this is exactly what happens with this landscape too. Okay, and when beta goes to infinity, you have this very particular thing. Okay, and so the way you should interpret this graph is that, so we have this rescaled time, we reach 1 in finite time in this rescaled time, and you have jumps. So these jumps correspond to particles colliding, okay, getting close. They cannot collide for finite beta because you have Cauchy-Lipschitz. But when beta goes to infinity, you expect them to collide because it's a singular limit. And then you have no movement, very, very low movement, exactly like we saw in the simulation. So you have jumps and plateau, jumps and plateau. And so this is generally, people call this dynamic mental stability. This also happens in models in physics, so PDEs. This is where I took the name from. So let me state the theorem. Let me think about how I state this theorem. So this is definitely not what you will find in the current version of the paper, but it's the actual result, which will come out very soon, I hope. Maybe I erased this. So you can look at the theorem. It's pretty hard to parse, but I'll try to explain it. And the thing that matters to understand the proof and actually the theorem is that this is not going to be a result that is valid for any initial configuration. So the thing I told you about convergence to global maximum is for almost every initial configuration. Here you're going to have to make a bit more structure. So what is the assumption? So you take X naught is well prepared if there exists a sequence of partitions P0, PL of the set of indices such that the first thing you have is that for any L between 0 and L, so these are partitions of the indices, okay? So it's a set of blocks. The thing you're going to have is that there exists a unique pair. So let's call it BL and CL. So these are blocks which are a subset of PL, which achieves this argmin. Okay. So the distance, this is just the geodesic distance on the sphere. So this is arc cosine of the angle of 2 points. Okay, I take 2 points, I look at their angle. The arc cosine is defining me the distance. And so basically what I'm saying is that at every step L, there's a unique pair of blocks which are the closest together. Now these blocks can have multiple elements, but it's a unique pair. And the important assumption on this pair is that really there's a geometric assumption, which is, let me state it properly. which is that if I note delta L, which is the distance of BL to CL, distance meaning this. So I overload this notation, but it's the distance between blocks. Then, and I take d prime L, which is the smallest distance of other blocks. Then we have that the cosine of delta L over 2 is greater than the cosine of delta L plus there's a constant, and there is a beta 0 such that this is greater than this. Okay? For any beta greater than beta 0. Okay? So this is the assumption we're making. Now, okay, this looks overly complicated, and I haven't even gotten to the statement of the theorem yet. But let me tell you what this means. Why the proof is kind of difficult. Because the proof is difficult because you want to do an induction, right? You want to do an induction argument. You're first going to look at the initial configuration, and you saw that in the simulation, points that were close, they got closer, right? But then what you want is that these points that are close, they get closer together. So you want to do an induction over this clustering, over this collapse. And to do an induction, unfortunately, the assumption we're making in this initial condition is that we are a priori imposing the merge tree, okay? And this merge tree is done through binary collisions, okay? So I'm only doing binary collisions. Okay, the thing I have to say here is that P0, so the initial partition is just everyone. And the final partition is the singleton. Okay, so this is really the merge tree. I start with all individual particles which are different. So I start with my point. Let's work on the torus for simplicity, but you can imagine that this is true in general. And geometrically, what this is telling me is that I have configurations which are already in a kind of pre-clustered form, but it's not too violent. It's just telling me that so when I look at these individual particles, these two guys are closer than these two guys by some kind of an exponential factor. And these two are much closer than this guy is to the other guy or this guy to the other guy. This is what this is telling me. And so essentially, I immediately know by this algorithm, which defines my initial condition, that these two guys should merge first. So I get a new partition. Before these guys merge, before these guys merge, before these guys merge. And then I get to the final point. And collisions are binary in the sense that at initial time, these guys may collapse, but then there's the blocks are only going to collapse block by block. I cannot have that these two blocks collapse with this guy at the same time. They have to first collision first. Okay? This is what this initial condition is telling me. And then what the result is telling me, so the result, the general idea is the following, is that you can prove, because of this initial condition, that so it's a result which happens when beta goes to infinity, but you don't have to take the limit. But if beta goes to infinity is a bit nicer. It's telling you that there exist finitely many times, actually L plus 1 times, capital L plus 1. It's exactly the number of partitions we have. There exists L plus 1 times. These are the merging times. So these are these times. Exactly this time, this time, this time, and this time. Okay? So there's L plus 1 times, which are independent of beta. And there exists limit curves, theta which are defined on these intervals, open intervals, so beyond the merging times, such that if I look at the empirical measure, so mu beta of t is 1 over n sum j from 1 to n of xi tau beta of t delta. Okay. So if I look at this empirical measure along this accelerated clock, I'll tell you what this accelerated clock is. This empirical measure converges in a narrow sense when beta goes to infinity to an empirical measure, another one, which takes into account the number of points that have collapsed in that zone. Okay. And then things just move on this plateau. Okay. You have these constant guys on this plateau. Okay. So that's exactly what I'm saying, that when I look at these particles, when beta goes to infinity, on every time I have as many. So this is just telling me how many clusters there are. Okay, in each plateau. So I look at how many clusters there are, and I reweight the empirical measure by this, and I have a few particles here. Okay. So that's number one. And number two, the second thing is that not only that we have this convergence of this empirical measure, the other thing we have is that the energy E beta along this empirical measure, so the rescaled on this rescaled clock, the energy converges to this piecewise constant curve. Okay, so there's some limit energy which is evaluated on this limit curve. Okay, and this limit energy, what is it? It's exactly summing the number, the how many points have collapsed at that plateau to the square. Okay. Okay, it's a complicated statement, but let me try to, at least for the people who are a bit more familiar with other phenomena, let me try to put it into context to explain you why you can expect something like this to hold. Actually, it just so happens that what we're showing is very analogous to what's happening in models like Allen-Kahn and Kahn-Hilliard. Okay, so what happens in Allen-Kahn and Kahn-Hilliard? Let's focus on Allen-Kahn, which is just this scalar 1D PDE. It's a gradient flow in L2 of a non-convex function, which is the scalar Ginzburg-Landau energy. Okay, it has two global minima, it's gradient descent, two global minima, +1 and -1. Okay, constants. And you can prove that you're going to converge to this global minima. Okay, one of them. But the way you converge is, again, in a very similar way. You have this coarsening, and exactly what we're doing with this model is also coarsening. Okay, so this is Kahn-Hilliard. It's not Allen-Kahn, but just to make the idea, it's you start with an initial configuration which is far, not too far, but far from the global minimum, and then you see that what's happened. So maybe I can show the picture. So on -1, 1, you start with maybe something like this at the initial time, and then what running this PDE is telling you is that points that are the zones that are positive. So this is maybe 1, this is -1. The zones that are positive are going to go here. Okay, so these guys start becoming a bit constant. The zones that are negative are going to go to -1. And then you have walls that are created. And the walls are of size epsilon. Okay, epsilon is exactly the scaling that appears there. So these guys are a size epsilon. And so what people showed for this model, there's multiple results. But essentially they go in the following way. We have a first set of results, which tells you, for instance, there's this paper I really like by Felix Soto and Maria Reznikov, Maria West-Dickenberg. But the same results were known already by Carr and Pego, and these are things that are known since the late 80s. There are results that tell you that you really have this slow motion in the sense that you start from an initial configuration, and you get stuck in this zone which is called the slow manifold of almost minimizers. You get stuck in this zone for a very long time, exponential time. So basically you need poly time to reach this zone. You reach this zone fast, but then you stay there for a very long time. And there's a way you can prove this. I mean, I can maybe talk about this later if I have time. There's very nice variational ways, energetic ways in which you can prove this kind of result. But this is one result which people prove. Then this is for fixed epsilon, right? So this is epsilon is the size of these walls. This is for fixed epsilon. You can also iterate this argument. So this is the first argument even we are using in the proof, right? Because we first have to say we're going to go to almost maxima, which are clustered configurations, okay? And then we stay there for exponentially long time. And this clock is an exponential rescaling so that everything happens in finite time, basically. So then people did an induction of this argument, of this auto argument. I don't know of a lot of papers about this. I know that there's a paper by Ekman and Rougemont in 98, which is not stated exactly in this way, but I think they claim to do this kind of induction. So this coarsening is really proven over all time. So that's number 2. And number 3, there's another series of very deep results, which also works for Cantillard, which tells you what happens when epsilon goes to 0. And so when epsilon goes to 0, meaning the size of this wall, what is the motion of this? So the first thing you know about the Cantillard energy, the Ginzburg-Langmuir energy, is that when epsilon goes to 0, it has a gamma limit, okay? The gamma limit is the perimeter function, okay? Now, there's another set of results, powerful method by Serfati and Sandier, which tells you that if you have a gamma convergence of an energy under some assumptions of the flow, so the PDE, you have what is called gamma convergence of the entire trajectory. Okay, so even the trajectory converges to a gradient flow of the limit energy. So what this tells you is that for Cantillard-Alencon, when epsilon goes to 0, the energy along the trajectory converges to the perimeter evaluated at the gradient flow of the perimeter for any time. Okay, and gradient flow of the perimeter is just the mean curvature flow. Okay, so this is the kinds of results you can show. But this is for a fixed time interval when epsilon goes to 0. And then you have epsilon fixed, t goes to infinity, you have the entire cascade. And what we're doing here, in some sense, because of this particular rescaling, is doing both at the same time. So because if you look at this energy, which is not very easy to understand, I'm sorry about that, but this energy, if you look at our energy, which is, okay, that's too bad, but if you look at our energy, if you look at it on any configuration on the sphere, the gamma limit of this is trivial when beta goes to infinity, okay? But if you look at it on these very particular configurations, then the gamma limit is exactly the number of clusters you're going to get in the first partition, okay? But it's still constant, meaning that the gradient flow of this is just trivial. So what this time rescaling is, so it's much easier in some sense than Ginzburg-Landau because everything is just constant. But because you rescale time, you're not a gradient flow anymore because you have this time rescaling which appears. And then you can kind of cheat so that you still get something non-trivial in the limit. Okay, maybe I will conclude. I want to conclude with a couple of things. The first thing is that I simplified the parameters a lot. In particular, I only looked at gradient ascent. You can ask yourself what happens when you do gradient descent. So when you do gradient descent, you're minimizing this energy. And what happens when you minimize this kind of a repulsive force on the sphere? You're going to try to distribute points uniformly, okay? And it just so happens that global minima of this energy are sphere packing configurations, okay? So you can recover sphere packing configurations, and proving that you converge to a global minimum is much harder. Actually, it just so happens that in the mean field case, n goes to infinity, the story is much easier because you have the uniform distribution. But for finitely many points, nobody knows how to prove this. And maybe I'll stop here. Thank you.